We shall continue our discussion on generalized angular momentum in quantum mechanics. In the earlier class, we have assumed a representation, or we represented a kit as JMJ, which is the simultaneous eigenkits of J square operator and JZ operator. And we found that the matrix element J prime, MJ prime, J square operator, JMJ, this is H line square J into J plus 1 delta of JJ prime, delta of MJ prime, and J prime, MJ prime, JZ, JMJ, this is also a diagonal one, MJH cross delta JJ prime, delta MJ prime. And for JX, we found that J prime, MJ prime, J plus JMJ, this was MJ prime, and for J minus these were the summary of the earlier class. Now, if for a given value, we have shown that for a given value of J, Mj ranges from minus J to plus J, that is a totality of 2J plus 1 values. But there is in fact no restriction on J. So the matrices are of infinite dimensional matrix. If we are to write the matrix for J, we write J square operator, the matrix for J square operator, we subdivide the entire matrix into different allowed J values. Say for example, J is equal to half 0, J is equal to half, J is equal to 1. If J is equal to 0, then the number of MJ values is 2J plus 1 is 1. So we will have only one value. So we write the matrix as this has only one component. For J is equal to 0, this is only one component. If we have J is equal to half, then the values is 2J plus 1. So it will have 4 components. So this is the matrix. I will calculate the matrix afterwards. Then if we have J is equal to 1, then we will have 3 values, these are the block diagrams of the matrix, and this matrix goes on increasing in this fashion. Then if we have J is equal to 3 by 2, then we will have 4 values. So this matrix will be in this fashion. The matrix continues to infinite dimensional matrix. So to say, this is the block for J is equal to 0, This is the block for j is equal to 0. This block is for j is equal to half. This block is for j is equal to 1. This block is j is equal to 3 by 2. Similar things happens for other matrices, other operators. Now we want to specify the matrix elements. For j square, the matrix element is very simple. So if we have j is equal to 0, this value is 0 itself. And if we have j is equal to 1, the value is, sorry, this h line square was missing there. This is half into 3 by 2, so 3 by 4 h line square. So this is 3h line square by 4, and this is same for this 3h line square by 4. Then these two values are 0, as it is appearing from this, they are diagonal. If we use j is equal to half this value, j is equal to 1, the value is 1 into 2, so these diagonal elements is 2h cross. 2h cross square, and other values are 0. And for this value, this is 3 by half into 5 by half, so this is 15 by 4. These diagonal elements are 15 by 4, 15h cross by 4, 15h cross by 4, 15h cross square by 4, and so on. These are the matrix elements. Similarly, we can find out the matrix corresponding to JZ. We can also find out the matrix for JZ. If we want to find out the matrix for JZ, it will have such block structure. This is 0, and this is we take h cross common. So for this it is half, this is minus half, 0, 0, and this is the j is equal to 0 block, this is j is equal to half block, and then j is equal to 1 block. Sorry, this is plus 1. This is j is equal to 1 block, then we have j is equal to 3 by 2, so this would be 3 by 2, 0, 0, 0, 0, half, 0, 0, 0, 0, minus half, 0, 0, 0, 0, minus 3 by 2. So these are the block structures for these elements. We see that as we have chosen a representation, which is the representation is the simultaneous eigenset of j square and jz. So in this representation, both the operators are diagonal operators. The other quantities, if we want to express jx, jy, etc., since jx, jy do not commute with jz, although they commute with j square, since they jx and jy, as it doesn't do not commute with jz, they will not be diagonal one in this representation. So similar thing is applicable for j plus and j minus. We shall first find with this matrices for j plus and j square and jz, we now switch over our attention to the matrix elements of j plus and j minus, and from this we will be finding out the matrix element for jx and jy. Now we first choose a special case. This is j case. We consider j is equal to 0, so mj will have only one value 0. So the eigenket is jmj eigenket is actually 0, 0 eigenket. And if we want to know what is the action of j plus acting on 0, 0 ket, j plus acting on 0, 0 ket, it will try to increase this this value by 1, but which is not allowed for j is equal to 0, so it is a null ket. Similarly, j minus when operates on 0, 0, it will reduce this value to -1, but it is not also allowed, so this is also a null ket. So the matrix for j plus is a null matrix, and so is for j minus. So obviously jx which is half j plus j minus, it is also a null matrix, and jy is equal to minus I by 2 j plus minus j minus, which is again a null matrix. Now we switch over to the case j is equal to half. These are the interesting cases. J is equal to half. This situation may arise from two, as we will discuss, from two considerations. L is equal to 0, S is equal to half, that leads to J is equal to half, or we may have L is equal to 1 and S is equal to half. So this will lead to two J values, J is equal to 3 by 2 and half. So J is equal to half may arise from two situations. One is 0 half combination and 1 half combination also. However, here we do not bother about the fact how j is originated. We only assume that j is equal to half value. So mj has two values, plus half and minus half. So we define two eigenkets. One is the simple eigenket is half plus half eigenket, and this second eigenket is half minus half eigenket. So first thing is what j plus does when it acts on 1. When j plus acts on 1, it tries to increase the mj value by 1, which is not possible, so this is a null ket. Now when j plus operates on 2, this 2 state is minus half, it will increase by 1, so that the eigenket is basically one eigenket, and there will be a numerical factor involved in it, and the numerical factor is given by h cross. Now j is half minus of minus half, that is half plus half 1, and then this cancels into 1 h cross 1. So this is basically h cross 1 state. Now j minus operating on 1. J minus operating on 1 will decrease the mj value from plus half to minus half, so the eigenket will be 2 ket, and the matrix element is given by this. This is h cross J is half and Mj is J is half and Mj is half. So half of 1, this cancels out. So again it is H cross time 2. And when J minus operates on eigen K2, it will make the J value, Mj value minus 3 by 2, which is not possible. So this is an null ket. Now we come to the matrix for J plus matrix. J plus, this matrix is for J is equal to half. The representation is that this is 1 1 element, then 1 2 element, 2 1 element, 2 2 element of J plus. We denote this element as this Ket1 is the second index and the first one is the bra index. So that means 1 1 means when we take the scalar product with 1, so this is a 0. H cross taken common, this is 0. Then this one, and this is again a 0. Now we multiply this with bar 1, so this is simply H cross. So H cross has already been taken common, so this is 1, and 2 2 is 0. So this is the matrix for J plus corresponding to J is equal to half. Now the J minus matrix is again with this convention. First one is when we multiply it by bar 1 is 0, and H cross I am taking common, this is 0. And when we multiply it with bar 2, it is H cross, and this, so this is 1. This part is 0 identically. So this is the matrix for J minus corresponding to J is equal to half. Now coming to with this we come to J plus, Jx. Jx matrix is half of J plus matrix plus J minus matrix. So we take H cross by 2 common, then this is 0 1 1 0. Recall that this is sigma x, so this is H cross by 2 sigma x Pauli spin matrix. Now coming to JY matrix. JY matrix is minus I by 2 J plus matrix minus J minus matrix. So we take minus I H cross by 2 common, and then this minus this, so this is 0 1 minus 1 0. If we take minus IH cross within this, it becomes H cross by 2 0 minus I plus I 0. This is H cross by 2 sigma y. So we see that for J is equal to half, the Pauli spin matrices has been reproduced, and JZ for this representation, JZ matrix is taking H cross by 2 common. This is simply So we could justify the occurrence of Pauli spin matrices from modern theory of angular momentum. We see that these are nothing but the Pauli spin matrices which were introduced before the advent of quantum mechanics. Now we switch over to the case of j is equal to 1. For j is equal to 1, there are 3 mj values. Three mj values, they are plus 1, 0, minus 1. For j is equal to 1, mj values are plus 1, 0, minus 1. We define eigenkets as eigenket 1 is 1, 1. Then eigenket 2 as 1, 0. And eigenket 3 as 1 minus 1. These are the 3 eigenkets. This is minus 1 minus 1. J plus operating on 1 will increase the mj value by 1, which is not possible here because the maximum mj is plus 1, so it is a null ket. Now j plus operating on 2 will increase mj value from 0 to 1, so it will be an eigenket 1, and the constant factor is h, and here this is j minus mj, so 1 minus 0 is 1, and this is 1 plus 1, 2, so this is root 2h cross 1. Let me again explain. J is 1, mj is 0 for this state, so this is 1 minus 0, this is 1 plus 0 plus 1, so this is yes. And j plus operating on state 3 will increase the mj value from minus 1 to 2, so the eigenket will be a 2 eigenket, and the factor is, here you consider that mj value is minus 1, so 1 minus of minus 1 is 2, and it is 1, so again it is square root 2h cross 2, eigenket 2. Now let me study the operation of j minus on this eigenket. J minus operating on this on one ket will reduce this value to 0, so it will basically a 2 eigenket, and the factor will be this one j. This is 1 plus 1, 2, and this is 1, so square, this is 2 square root h cross 2. Then j minus operating on state 2. This is 2 means mj is 0, so it will be an eigenket 3, and the factor is 1 into 0, 1, this is 1 plus 1, again square root 2h cross 3, and when j minus operates on eigenket 3, it will drag the mj value from minus 1 to minus 2, which is not possible, so it is an 0. So we are after the matrix element of j plus operator. They are 1 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. So this one line will come from this, and we take root 2h cross common because whatever the non-zero factors are root 2h cross. So this column will originate from here. Since it is 0, these matrix elements are 0. then these two elements will originate from one here. When we multiply with ket 1, this is 1. When we multiply with ket 2 is 0. When multiply with ket 3 is 0. And coming to this one, this is when multiplied with ket 1 is 0. When multiplied with ket 2 is root 2h cross. So this is J plus, and J minus matrix is root 2h cross, and these matrix elements are, this will be the 0, 1, 0. Then coming to this 0, when for 1 bar 0, 2 bar 0, and 3 bar is 1, and this is 0, 0, 0. So this is the J plus and J minus matrices for J is equal to 1. And the corresponding Jx is Jx matrix is this half factor will make it h cross by root 2 and sum of these two matrices. So this is 0, 1, 0, then 1, 0, 1, then this one 0, 1, 0, and Jy matrix is minus I h cross upon root 2, and this minus this. So first is 1, 0, 1, then minus 1, 0, 1, and then if we arrange this, h cross by root 2, 0 minus I 0 plus I 0 minus I 0 plus I 0. This is the Jy, and Jz is a very trivial one, is h cross 1, 0, 0, 0, 0, 0, 0, 0, minus 1. This is Jz. So we have obtained the matrices for Jx, Jy, Jz. Jx, Jy, Jz, and J plus, J minus, and of J square for few low values of orbital angular quantum number J. To bring this discussion towards an end, we just outline how to calculate the matrices for J is equal to 3 by 2. Now the last example that I am going to consider is J is equal to half, and J is equal to 3 by 2, and we shall find out how the matrices are. So for J is equal to 3 by 2, Mj values are 3 by 2, half, minus half, minus 3 by 2, and we define the kets as ket 1 as 3 by 2, 3 by 2 as ket 1. Ket 2 is 3 by 2 half. Ket 3 as 3 by 2 minus half, and finally get 4 as 3 by 2 minus 3 by 2. We first study the operation of J plus. J plus operating on 1 tries to make it 5 by 2, so it's a null cap. Now J plus operating on 2. J plus operating on 2 will increase the projection from half to 3 by 2, so it will be an eigenket 1. Now what will be the factor? Here J is equal to 3 by 2 and Mj is half. So this factor is 3 by 2 minus half into 3 by 2 plus half plus 1. So this is 1, this is 2. So this is root 3 H cross. Now J plus operating on eigenket 3. Eigenket 3 is this, so it will increase this projection from minus half to half, so the eigenket is basically a 2 eigenket. And what will be the value? This is 3 by 2 minus of minus half, so this is half minus of minus half, then we have 3 by 2 minus half plus 1. So this is 2 and this is again 2. So this is 2 into 2, so this is 2H cross. And J plus operating on 4, it will increase this value to minus half, so the eigenket basically will be the 3 eigenket, and the value is 3 by 2 minus of 3 by 2, so this is 3 by 2 and this is into 1, so this is root 3 H cross. These are the eigenvalues. The evaluation of J, operation of J minus on these states are left as an exercise, and I am going to make the matrix, construct the matrix corresponding to J plus operator. You recall that it is 1 1 1 2 1 3 1 4 2 1 2 2 2 3 2 4 3 1 3 2 3 3 3 4 4 1 4 2 4 3 4 4. These are the matrices. Whatever may be the factor, for non-zero factor H cross is common. So this is. This 1 originates from this line, so these are 4 zeros down the column. Then the second column is originated from this. It will have root 3 when bar is 1 and 0 in other cases. Now coming to this will have only non-zero value for when it is dotted with bar 2, and so the result is 2 . This is the matrix corresponding to J plus for J is equal to 3 by 2. With this, we end our discussion on the generalized angular momentum. In the next class, we shall extend the concept to this concept on further discussion of angular momentum, that is how to add two angular momentum of, that is the addition of angular momentum. Although the theory is very mathematically involved, but we shall avoid the mathematical rigorosity and will rely on the physical justification to build up our working principle for the addition of angular momenta.